Good afternoon, everyone. I think my screen is visible. You can see the first slide. Okay, great.
Yeah.
Great. So, where we exactly ended yesterday is we have seen yesterday was our first class for QT-01, and we have seen that what is the requirement of emergence of quantum technology over the existing one. We have seen the current pitfalls in computing in terms of storage, in terms of time, as well as some of the computational challenges that we have. So we have seen all those challenges, and we also have seen that one challenge was our inability to model some system which is not under our control, that is not in the macroscopic world. Something that is happening very naturally or something which is very much of a non-deterministic, we cannot really capture their properties or characteristics. So these were the pitfalls, and then we've seen that quantum computing offers certain great amount of speed up with its unique quantum mechanical properties like superposition, entanglement, and all those stuff. So today, I will exactly start from that point. Today, primarily we will be covering where we ended. That is it really the case that we will not be understanding quantum? So what is what do we mean by the famous scientist Feynman's that question that you cannot really understand a quantum mechanical system fully? What do we mean by that? And what is the probabilistic outcome and all those things? So today's class is going to be a mixture of a few things from QT-01 I have picked up, which is a part of a classical physics, which we will be covering, followed by the hardcore quantum physics, the mathematics of quantum physics or quantum mechanics that we will be covering. And if time permits, then third part will be where we will be actually seeing how the quantum states or that particular thing, how to construct that particular quantum state. Okay, so that is a part of computing. So today we will be covering primarily three different verticals in that kind of a storytelling way, where we will start with the classical physics, followed by the quantum physics and few postulates of quantum physics, which is kind of a building block for quantum computing. And third one will be that how that all those things can be used, or introduction you can say, of that quantum states and all those kind of computing stuffs with that quantum physical properties. We will be seeing those things probably. So that is our kind of an agenda. So this is just a quick recap. We have seen it. I just have included this slide so that for those who maybe have not done any brush up, so it is a kind of a brush up for them. So I'm just skipping this. I hope you can remember this. The superposition was the property of a quantum mechanical system to be in multiple states simultaneously. We also refer it as a probability to exist in more than one state, or we can say it's a abstract mathematical possibilities. Okay, representation of an abstract mathematical possibilities that can exist simultaneously. So anyway, we can define it, right? But in how mathematically superposition you can realize, we will cover in the third part. Okay, so just hold on for that. Entanglement also, we have seen that some sort of correlation between two quantum particles, that is called an entanglement. But theoretically, we believe that even if they are light years apart, there will be certain amount of a correlation. Einstein actually first denied the fact because of the theory of relativity. It is against that. But actually, for communication, we use entanglement, but that is not the theoretical definition of an entanglement, that they can actually be the light years apart. That theory will not work because of the decoherence and all this stuff. Okay. Then comes the quantum interference, the rounds of probability waves, where we have seen the double slit experiment. Two waves, if they align with each other, they will form a bigger wave, which is a form of constructive interference, where multiple quantum states will be added and each state's probability will be reduced. And another one is the waves cancelling out each other, which is called the destructive interference, where we have seen that quantum states will disappear, they will be deleted, you can say in that way. But the probability of the remaining states will automatically be increasing because the total probability, normalization constraints, and all those things, the total possibilities has to be one. It has to be exhaustive that way. Okay. Now cloning theorem. Again, theoretically, we have seen that. So today we will be covering the superposition and entanglement both in our third part of today's lecture. Some of the mathematically we will cover. No cloning theorem specifically we will cover with quantum teleportation. So this will be covered in a separate chapter. But a quick recap of no cloning was where we believe that an arbitrary quantum state, unless it is a very special state, I defined the term special. What is special? We yet have not mentioned that, but unless it is a very specific kind of a base condition or a special case, arbitrary quantum system cannot be cloned. So an intruder or an eavesdropper cannot really clone a quantum system. And so man-in-the-middle attack in quantum computing or quantum cryptography is not possible because of this particular very strong property of quantum physics. Okay. And quantum decoherence, it is a slowly or gradually kind of a diminishing feature of the quantumness that can arise because the quantum systems are very much fragile and they are, with respect to the environment, they are very kind of, there are a lot of coupling errors that can take place. Two neighboring qubits often cancel out each other's quantum property. Non-interacting qubits, if they are placed, say, in a neighboring configuration, so the interacting qubits, if they are far away, then in order to reach to that particular desired qubit with which the first qubit is interacting, if that is a far distant, at a far distance, then also they will lose their quantumness. Okay, so all of and these are just the two cases. There can be a lot of other cases where the decoherence can cause a real issue with the quantum computation. So what we should keep in mind is that I mentioned that two things here the researchers are focusing on. First thing is that they are thinking of an error correction code, and second one is if decoherence exists, they try that how their computation can be safe even if there exists a decoherence. For those things, they are actually referring some of the routing strategies of qubits, some of the configuration in the hardware level in a way, or some algorithm or logic to be developed in a way so that the communication can be faster, so that the chances of decoherence is very less. Okay, even if I am fragile, if I work very fast, my work is done, I am generating my throughput. After that, if I decoher, then that will not be an issue. So similar kind of an idea is being incorporated over here. And why these principles are making this thing revolutionary? Of course, they are all providing us a quantum advantage in terms of speed, in terms of like storage, in terms of cryptographically secure methodology, all those things. Except the decoherence. Decoherence is a challenge. It's not very advantage, but it is giving, but rather it's a challenge. Okay. Okay. So now the question was, so for these are few slides which I've taken from QT-01 course. So those who have it, probably they will be having it. But for today's lecture, I thought that a few parts of classical physics, though it was not a part of it, but a few part of classical physics is better to be included over here at least, so that you get some theoretical knowledge of these things as well. So like classical theory predicts that the black body radiation should emit infinite energy at high frequencies. But Planck's hypothesis, it is known as, so Planck actually discovered that energy is not a continuous thing, but it is quantized. Those who are from the, like, have some good knowledge of classical physics, all of you should be well aware of it. I will not put much time here. So just remember the formulas and all. Just a quick recap. H is the Planck's constant. The mu is the radiation frequency in terms of hertz, and E is the energy of one quantum in joules. Okay. So these are a few insights which are there. So our insight was from this thing, Planck's breakthrough was that light behaves as an individual energy quanta or as a photons, not just as waves. Okay. Photoelectric effect, light behave as particles. Okay, so classical prediction was that increasing light intensity should eject more electrons, regardless of the frequency. But in reality, Einstein discovered that electrons are only ejected if the light's frequency exceeds a particular threshold, no matter what is the intensity. So conclusion was light is not just a wave, rather it behaves as particles or photons carrying some significant amount of energy as well. Okay, so different aspects are here being proved, that how the classical physics failed and how the quantum physics actually overpowered classical physics for a few particular scenarios. Okay. Third one was Compton scattering, which proved that light has momentum. So initially, classical physics said that waves have no momentum, but experiment showed that, okay, it actually, like light behaves like a particle with momentum, contradicting the classical wave only explanation. So it has also momentum. These are few properties of light. And for a detailed explanation for these slides, please refer to, I guess it was on lecture 2 or lecture 3 of QT-01. Since it is just a recap, so I don't think audio is breaking for everyone. So if it is just since it is just a recap, so I'm just putting it in a fast way. If you want, you can definitely watch the videos for the detailed explanations. The fourth one was the ultimate shock, that the double slit experiment, which shows that yes, the interference pattern, which I explained, I just explained that there were two slits, and light actually instead of like instead of creating only two bands, okay, it is creating a lot of other bands, and their intensity and their band, what should I say, the thickness of the band, that is also not constant. Okay, so difference in the interference pattern actually defines that there is a chances of a constructive and a destructive, where out of the two slits, whenever lights are emerging in form of wave, few waves are aligned with each other, creating some thick pattern or thick band, and few are cancelling out each other, creating a thin band or thinner band, right? Okay, this also you can see. I'm not getting into it today because we have a lot of things to cover. Time permits, I will again come back here. So black body radiation and Planck's hypothesis. So Max Planck's hypothesis, you can go through that. And for those who will go through it, see, two slides per theory has been provided to you. So energy is quantized for that, the black body radiation and Planck's hypothesis. So what was the original story and what was the final observation? Likewise, it is given. All these slides are already there. So second one was a photoelectric effect and Einstein's quantum light, which is lights made up of particles of photons. Then photons have momentum like particles, all the four things that we just discussed. Okay, a bit more explanation, theoretical explanation of those things. Here you can find. And last one is the double slit experiment or wave particle duality feature. Got it? Okay. So post that, looking into the different strange or bizarre properties of light, there are definitely some kind of a newer explanations were needed, and accordingly, the theory of no audio. Is it really so? Am I not audible? Audio is okay or not? Audible. Okay. Thank you. Thank you. Thank you. Thank you. So post that, the classical physics actually failed to discuss or say describe a few properties of light, for which we actually slowly got inclined towards the quantum one or the quantum mechanics. Okay. Now, so now, what I will talk today I will be explaining things, giving you notes on the go. So just try to have it. So just a quick summary if I want to have. So from yesterday's class and just today, whatever I discuss now. So quantum physics, it describes an object, say, description of an object. So just a summary, you can say, or kind of the full picture. Okay? Describes an object in form of a wave function. You can say that. Right? Now, wave function, whenever from quantum, it is actually coming in our world, which is on, say, measurement, we can actually see the particles form of it. It is a part of the wave particle duality. So initially here it was a wave function, it is a particle, and this is a quantum physics initially. It describes, okay? And how we are getting the particles? Some property or say some mystery that we can see over here is due to the measurement. Measurement rule. What is the mystery regarding measurement? That mystery is on quantum measurement or on measurement of some quantum state after certain number of operations, we will see that the outcomes are really very uncertain. Okay? And the order of the outcome means the result that we are getting. In what way we are getting results? I'm not going into that. It is in form of a quantum state itself. We'll describe what is a quantum state and all those things today. So, but the outcome or the result or the output that we are getting, they are very uncertain. That is, the outcome is not fixed or say not fixed. This is the first one. And second one is the outcome. What are the total outcomes? That is constant. But what exactly outcome will come? That is not fixed. Okay, so that means say I have in my say wallet, I have 10 rupee, 20 rupee, 50 rupees and 100 rupee note. But I do not know that on measurement which note I am going to get. That is unknown to me. This is the meaning of the first thing, that outcome is uncertain or it is not fixed. Okay, but definitely I know or I should be knowing that what are the total possible number of outcomes. It should never be like 2000 rupee note or 500 rupee note is there and I do not know about it. Or what are the notes I do not know. But which will be the outcome exactly, that I will not be knowing. This is the first property. Second property is that even if I say start taking some one by one all the notes, in what order the notes will come out from my wallet, that is also not fixed. There is no guarantee that 10, 20, 50, 100 it will be, or it will be 50, 20, 10, 100. So the order of the outcomes, that is also not fixed. This is the meaning of it. Any outcome can come. Anything can come. For a purely quantum mechanical system, our outcome can be anything. Just to give you a small example so that it is more relatable to all of you, a quantum state or a quantum state can store either a 0 or 1. Right? Now, if I just say that I will, if I throw or say a very small quantum example, just say for example, I have a coin, I want to toss it. So I know that what are the outcomes. Of course, it can be either head or tail. But once I throw it, until I see that what is the coin status, I cannot say whether that is a head or a tail. So it is perfectly uncertain. Considering the coin is not biased, or the way the coin is being thrown, that is also not biased. Because often that also defines that whether it will be a head or a tail. But considering everything is fair, there is no biasness, outcome of a perfectly unbiased coin is always properly uncertain, just like a quantum mechanical system. Okay. And order also is not fixed. I do not know that whether it will be head tail or it's a tail head or it's a tail 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 tail. Likewise, anything I can get. Great. So now you understood, or you should be able to at least figure out that, though not mathematically, but yes, this is what Feynman mentioned, that you can never know you can never know quantum mechanics in that way. If you think you know it, then you don't know it, kind of, because it is always very uncertain. Okay, so with regards to measurement theory, he stated that thing. It does not mean that it is very difficult to know. We cannot learn it. He did not know it fully. Nothing like that. It's just that no matter how much try you give, the contextuality of your preparation, the way you prepare your quantum state or quantum system, and the way you can measure, that is the preparation contextuality and the measurement contextuality, they are never aligned. If you fix one, the others will automatically be changed. There is no way you can fix it up, both the things. If you just define that this is exactly going to be your measurement outcome, then definitely on preparation level, there has to be some non-contextuality. So they do not align with each other. That is why we can never get our desired measurement or our desired outcome until and unless we do certain computing. See, measurement, factor, phenomena, all these things are from part of quantum physics. Put it an end here. But whenever you are using all those properties in order to write your own quantum algorithm and you are using measurement, then you definitely need to do two things. One is, on that quantum level itself, you have to put some quantum logic in a way that it can perform some constructive interference or destructive interference of a few quantum states, either addition or deletion, so that ultimately you get your desired outcome. Right? So those who attended the I will. Whatever question you have, we will discuss at the end. Okay. So if the ones who attended the Grover lecture in QT-01, if you can remember, we were talked about the quantum amplitude amplification. Okay, with Grover, where we started with all quantum states, and eventually, with course of time, we actually were slowly heading towards finding one state as our desired output. And you've seen that how difficult it was, like how many steps we have to do for all those, like quantum Grover rotation operator, under which there were two different types of operator, the geometric interpretation, the number of iterations, how much we have to do, all those things. After that, we get our desired output. So definitely you have to do that. Until and unless you don't do anything, it will be perfectly uncertain. In order to make it working in your own way, you have to do certain amount of tweaking. This is the first thing. There is a second thing. If you want to get your desired outcome, there is a second thing. And quantumly, maybe you are not doing anything. You have got all the outcomes in whatever way you are getting. Maybe that is uncertain. The order is also not fixed, but you got all the quantum steps. That is also correct. But maybe out of those steps, only one or two steps should be your output. Then once you've done quantum like measurement, it will now boil down to classical. Okay, now we have to do some post-processing. Okay, so measurement problem is here. There are two possible solutions on computing level from computing ground. Okay, and the selectively incorporate interference. There is no logic for that. You have to define your own logic based on your algorithm. Second one is use classical post-processing. After measure. Okay. Now, wave function, since it behaves as wave function, it also has a certain amount of consequences. What are the consequences? All those things. The first one was superposition, followed by entanglement. Then it's uncertainty principle. Okay. Heisenberg's, let me write Heisenberg's uncertainty principle. It states that position and momentum, how to write it? Say versus and cross. Okay. So they are not aligned. Cannot measure both position and momentum in a static way. It is not possible. Energy quantization and all those things. There's one more thing which is called a quantum tunneling. Okay. So this is quantum physics in a nutshell. I'll just describe quantum tunneling, then I will proceed. This is, you can say, quantum physics in a nutshell, so kind of that. The entire picture, the whole picture. And the summary. Say. Okay. Now, I hope till this part it is okay. Now, just one thing, the quantum tunneling, I just want to describe it once. Quantum tunneling is since we actually since we believe that quantum behaves in a wave form. So even if there is any, say, for example, tunnel, kind of that, we believe that initially, if it is a non-quantum particle or a non-quantum system, then it will stuck here because it cannot pass through the tunnel. Okay, but so it will be in this particular position, has 100% probability. And here it will be here. This has 0% probability. Where if it is a classical setting. But if it is quantum setup, then we believe that we can actually tunnel through because it's just a wave. Maybe here it's a 30%, here it's 70%, or say maybe 60%, here it's 10%, but it will ultimately be in a wave form and it will exist likewise all through the tunnel. That is quantumness. Quantumness, because of the wave property, it is believed to be tunneled through some kind of system. Okay. So, and this has an application in phases of where we stuck in local optima. Stuck in local optima. This particular problem will not arise in quantum tunneling. But this is the problem in stucking in local optima is something that which is there for simulated annealing. Okay. Any question till this part? I can pause here for 2 minutes. Any question till this part? We can clear it now, then I will again proceed. Anyone else? Someone was asking some question. You can ask now. On measurement, someone was asking. Repeat tunnel. Sure. Sure. So there was a story. If you do not know or know, I don't know, simulated annealing. So it is basically, you don't understand simulated annealing. It's not stimulated, it's simulated. Yes. Okay. Okay. So the picture is something like that. Say, for example, you are in a kind of a ground. Okay, where there are several this kind of thing. So say something like that. Let me draw some abstract image. I'm just trying to, maybe you will understand it. Just try to understand it. I'm very bad at it. Say these are small kind of hills kind of thing. Collapse of wave function collapse, all the maths will come. Just hold on with the maths. Just ask me any question without maths, because just after this we will be covering all the maths. So say for example we are such ground where I am here. I'm a particle, say, or I'm a very small person. I cannot see anything. But once I climb through the top, then I can see something. Likewise, say I am in a position where I do not know that where exactly, say I am in a particular position, I do not know that what is the best minimum to that. Maybe the diagram was something like that. Say for example here, I am in a position where I am thinking that okay, so I got this one, so this is my minimum. Because out of all the existing one that I got, I have seen that okay, this is the minimum thing. But maybe just after that, some sort of this thing exists. But once I'm here, every time I will think that where I'm stuck in, I will think this is my minimum now. But is it minimum? No, because this is minimum. Actually, this part is minimum. Okay, but in these kind of structures, we are always stuck in this. Due to this, we are stuck here. So physically, someone just um, climbing some hill or something. So wherever he is right now, he's thinking that okay, that is the minimum point. That is the minimum. So he or she can never find the global minima or the global optima. Every time they will stuck in the local minima. And this is a problem for simulated annealing, which is a technique used in artificial intelligence and for some of the problem solving. Just like ant colony optimization is a technique, or say particle swarm optimization, this is another technique. Okay. So for those things, that was a challenge. That was a challenge in classical. Because often for a lot of problems, we define that the ground state energy or the minimum state energy or state with the minimum energy is always our solution. That is how we process our like entire algorithm in a way that wherever we get the minimum one, that is our desired outcome. But often there can be some computational challenge associated with that, because what we think our minimum to be, or maybe that is our best case to give as a solution, say some portfolio or something, whichever demands a minimum thing or some optimal thing, which we believe maybe that is just due to we are stuck at somewhere and we are unable to see that whether there is any further minimum exist or not. In classical, this is known as simulated annealing. But in quantum, what I'm telling you now is in quantum, there is a theory or quantum technique called adiabatic approach, quantum adiabatic algorithms, which uses this theory of quantum tunneling. Adiabatic means the same thing. In a very easy language, I'm trying to explain it. There is a kind of an algorithm called quantum adiabatic algorithm, where our target is slowly, just adiabatic means slow, very slowly, just do a certain evolution of quantum state in a way such that the state will automatically convert to the lowest energy state. And that lowest energy state will be our solution. This technique can be used for optimization problems mostly, and we use this thing. Now here during this slowly convergence, if it is a simulated annealing for adiabatic algorithms, it's stuck in the local optima or local minima. You can see this thing. Okay, because of this, it will here from this position, it is unable to predict or unable to locate that whether there exists a better solution, which is an even more minimum thing than the previous one or not. But the thing is, for quantum, actually, I will travel through all both the things. So once I'm here, I'm also here. for quantum. Let me just choose a different color. Yes. So this is for classical, but once I am quantum, this is I am quantum. Say this is classical. See. So once I am in a quantum, I am a quantum particle. I will tunnel through because I am also wave. So once I am here, I am also here. Once I am here, I am also here. Likewise, now because I'm here, so of course I can say that, okay, no, this is not the minimum, rather this is the minimum. Now, once I get this one, I will again tunnel through this one. Likewise, it will traverse the entire search space and find out that what is my global minimum. And how? By ability to be tunneled through. Okay. So this is a logic. This is clear? Yes, it only quantum tunneling only is applicable to the quantum particles. All the particles which quantify themselves as a quantum particle, only on them this theory is applied because it is happening only because of the wave particle duality. So whenever a quantum particle is here, with certain probability it will exist here as well. Similarly, whenever it is here, it will actually tunnel through. Of course, it is applied to light. Of course, photon is a quantum particle. Definitely. For those who want some working model or not, I will just suggest, I think I am not sure, maybe in QT-05, we have details of again some quantum computing and algorithms. Okay, so there you will be getting some, in QT-01 also I discussed a bit more than what I discussed today because there was a scope of discussion of these quantum algorithms. So just go through the adiabatic algorithms of quantum. At least you will get the basic essence of what I have told to you. You can get the quantum like working model from there. But it's very useful for optimization problems like supply chain optimization, portfolio optimization, all those things. It is very much useful. Got it. Okay. Now, now next is, see, these are all the kind of building blocks. Okay. So, and these are lectures you recommend for your lecture. See, few parts maybe I have covered, few parts are covered in one session or maybe one QT-01, one series, maybe few are covered in other series likewise. But there are certain parts which will be covered here in a more detailed way. But few parts already, because of quantum algorithms, so I'm referring, na? So I'm referring quantum algorithms, few of the quantum circuits, quantum gates. So a part of it is very well described in QT-01 as well. So those who want to know the quantum, maybe I guess we discussed 3 quantum algorithms there. What are the types of it? These again will come, I guess, if I'm not wrong, I'm not 100% sure of it. Maybe organizing committee, they can say that. Maybe QT-05 or 6, again, they have those things in a much detailed way. So there you will be again getting that flavor. But some part of it you can see over here because suddenly I'm just bringing the adiabatic algorithm. So I just where there are different types of like quantum algorithms. So one particular category was adiabatic. And but quantum tunneling is a feature of quantum mechanical theory, and that is very much related to adiabatic algorithm. So for all those interrelationship, I have described you what I just described, the simulated annealing and adiabatic, just to give you the essence of what quantum tunneling is. Okay. Okay. Now we are entering towards the postulates of quantum mechanics. We'll cover a few postulates as well as we will see the maths for superposition, entanglement, and all these things. it's better to focus here very much. Few things I will be telling, few things even after, I guess, next class or next to next class also, few things I will share in a more detailed way. But according to the syllabus what we have, I'm just trying to follow that. I hope it is not a problematic, it will not be very problematic to you. I will be explaining. I will do the repetition. Repetition is not a problem. Okay. Please focus. If you want to take notes, just take notes. Otherwise, please put your full focus. Okay. So physical states here we represent physical. I'm not using different colors. I guess you all have the syllabus already. You already have the syllabus. So just that only I'm following. But of course, like the sub parts or sub modules under a particular session is not described there. So, but in one class, I'll be telling that what we will be mostly covering in the second class, because that was our agenda for to cover the postulates of quantum mechanics today, along with a few parts of the quantum physics. So I not put much time on that because I wanted to describe the few of the maths here. Okay. So now just focus. I'm not using different colors of this pen, otherwise it will be more time consuming. So physical states in quantum mechanics. Now everything, forget about classical, now enter into quantum mechanics. Now how the building blocks of quantum mechanics is actually there. We are going to understand those parts. If you want, I can share the submodules. Okay, today I will just after I end today's class, but tomorrow at least the detailed submodules I will be telling. I'll just write it down in the slide itself. You can check it over here. So physical states in quantum mechanics, they're represented by rays. All of the terms that I'm using, these are standard terms as described by the research papers and books. Okay, very standard books. So rays in Hilbert space. For those who attended, they know what is Hilbert space. For those who do not know it, it's a part of vector space. Okay, with a certain property. What are the property? It is a, let me write down, Hilbert space. Hilbert space. It is a normed vector space where the concept of inner product is defined. That is why it is very difficult quantum, because every term itself brings into picture another term. Okay, so that is the difficulty. All these things I explained, but again, in a very easy language. Inner product of two vectors are basically like in this way, say. Inner product of vectors are written in this. Okay, just remember it is a scalar product. Again, some of the notations have came. It's a scalar product. I'll try to explain. I'll try to. Okay. Where what is this thing is, this thing is psi, and this notation is known as Kate notation. This is a part of Dirac notation. Dirac is a scientist who defined this thing. And its dual of this Kate is basically this thing. Okay. It is also represented in this way, that it is called the bra notation. It is another Dirac notation. And together they form the bracket notation. Okay. Right. So this thing, the Kate form, is represented by a column vector. U and V are the vectors, but this is kth notation. This notation is used for other thing. There is a matrix representation of it. These are quantum states. I will try to cover that part. Right now, just slowly try to understand. If U and V are two vectors, and then this notation like ket UV, I mean ket U and bra U and ket V together, whenever we write it in a compact way, this is known as the inner product form. And this inner product ultimately give you a scalar product. Now, with respect to scalar product means just a scalar term, a magnitude, nothing else. Now, with U and V, it is very difficult to tell you that how it is. Let me just take an example. I'm just coming to that part. So this kth notation is a column vector form, and this bra notation, this is a row vector form. So inner product form is often, you can think it of in this way, that a row vector form and a column vector form. Kind of that. So now, just this thing, the row vector form and the column vector form. Say UV, let me write a row vector form and a column vector form. Right? So say I'm just writing U as U1, U2, and V I'm writing as V1 and V2. Then what will be the product? Okay, what it is? It's a 1 cross 2 matrix, and this is a 2 cross 1 matrix. Column vector is nothing but 2 cross 1, row vector is 1 cross 2. If you multiply it, what will be the end dimension? It is a 1 cross 1 thing, right? And definitely this multiplication is possible. So if you do that, 1 cross 1 means a scalar 1. So if you just multiply it, it's U1 V1 plus U2 V2. So this is a scalar 1. And this is called the inner vector, inner product form. Right? Okay. Now, order of vector matter. Of course, it will matter. Order of vector means in terms of notation you are asking, or what you are asking? You just check it. U and V. Yes. Why are you asking? Just cross verify it. Confusing. For scalar, it will not matter, but it will matter where I am telling you. V1, U1. In terms of magnitude, it will not matter, but it will matter where I am telling you. Often, these particular things associated with other vectors or other quantum states. So, directly, do not try to do the commutative, whether it's commutative or not. Don't try to go there, because it will not be there directly. These will be associated with some other vectors. So there it might be a problematic thing. Otherwise, the scalar output is same. But whenever we say it, we call it inner product, inner vector form of U and V in that way. And it means that U is in the following the bra notation and V is following the ket notation. That is a general convention. Okay, just follow that. Okay, now inner product of two vectors. What are the vectors? Say psi. Anything, I'm just writing psi itself, and phi. In Hilbert space, will be written as this thing. Right? Now, if they're identical, for identical thing, what will be it? It will be greater or equals to 0. And it will be 0 only when this psi is a null vector. Then it will be a 0. Otherwise, it will be greater than 0. Okay. Now, we are entering towards quantum state. Before that, we are just forming on the building blocks. We have got the Hilbert space. Now we are discussing all about the space itself. Okay, all of these are part of the postulates. So, first one is space is a linear vector space. What do you mean by linear vector space? So psi, inner product of psi and A phi 1 plus B phi 2, where A and B are simple amplitudes or say constants. This is the inner product of psi, psi and this entire thing. Okay. Now this is equals, we can write it in this way. Sorry. If you can write it in this way, then it is called a linear vector space. This is linearity. Okay. And psi phi inner product form star is basically this thing. Now you got it why I have just said that don't write it down in that way. Maybe the scalar value we are getting same, but the notation wise it might be complex for you to understand. So this is the dual thing. So dual of this thing. And this is called dual. And also inner product I just told all the details, these part details is there already as and when required. So you can check it out. For let me just write it down. What are the things? Let me just write it down. Dual is simple. I mean, bra is a dual of kit and vice versa. It's a dual of bra. Which means if this is, say, for example, 1, 0, okay, so this will be 1, 0, sorry, yeah, 1, 0, star, and it's often represented with a row vector, 1, 0, this way, individually, one star, but complex conjugate of this thing is nothing but 1, 0 itself. So that is why we write it in this way. And they are dual of each other. Please go through a few things from QT-01, inner product. First, it should be vector product space. I'm just writing in vector product. Then go through that thing, Hilbert space in more detailed way. I guess first 3 to 4 lectures. If you see from YouTube, it will be covered. And you should be watching it. And together it's the thing. Hilbert space and like plot sphere representation for more details. Plot sphere representation, entire theory of quantum states and all. And if you want, of course, quantum algorithm, I'm not writing it. Okay. And you will be finding these things probably in second, third, fourth, and fifth lecture, maybe. Second, third, fourth is, I guess, confirmed. We'll be finding it in detailed way. Okay. So space was a linear vector space. We have seen that. Now next is, just a minute, let me change the color, otherwise it will be clumsy. Issue with the other colors that you have. Yes. Okay, so this is the first one. Now we are entering into the second. Just stuck. Yeah. So should we tell this just a minute? Uh, just happened. Current slide. Oh, thank God. Yeah. Okay. So first one was space is a linear vector space. And now second property, we are heading towards that. I'm not removing or deleting any part of it, but please refer. When you see the lecture, please refer the flow that I'm like trying to maintain. Now say the vector space is a d-dimensional vector space. Okay, a d-dimensional vector space spanned by basis En. Don't worry, I will explain everything. So n is the dimension. Then psi equals to sigma n alpha n En. Can write in this way, and the basis may be chosen to be orthonormal, such that this inner product of Em and En is delta Mn, and alpha n is nothing but En, inner product of En and psi. A lot of things is written over here. Let us gradually show all the proof and understand it, that what it is, a lot of things are there. D-dimensional vector space, orthonormal thing, what is basis, inner product of Em and En, delta, a lot of stuff. Let us go slowly towards the proof. So first, let us explain for just a minute, give me a minute, let me just color it once, since this is the second one. Yes, so this one is second, and this one is first. Yes, so first, let us start with orthogonal versus orthonormal. In linear algebra, currently see now we are like massively using linear algebra to build the fundamental blocks of quantum mechanics. Okay. So when two vectors will be called orthogonal to each other if their inner product is 0. That is why we first discuss inner product, which is nothing but a scalar item. And orthogonal vector means if two vectors inner product is 0. That is, two vectors, say u and v, are orthogonal to each other if their inner product is 0. Now we know how to write inner product. So it is to be written in this way, U, V, with this symbol. If this is 0, right? So this means, what does it imply? This means that U and V, these two vectors are perpendicular to each other. Okay. Now, orthonormal means, to be orthonormal, if two matrices have two vectors have to be orthonormal, then first property is they have to be orthogonal. They have to be orthogonal to each other. This is the first property. And second property is each vector has unit length. Unit length. That is, their magnitude is 1. So in this way, so we can write it down in this way, that orthonormal is basically, that is how it is named orthonormal. It is nothing but orthogonal plus normalized. So orthogonal plus normalized is orthonormal. Now, few examples of this thing, orthogonal and orthonormal. Say example is in two-dimensional Euclidean space. I think Euclidean you all are well aware of. Normal like XY, all these things that we know. In 2D Euclidean space, say U is a vector which is in this way, say 1, 0, or 2 cross 1 column vector, and V is say 0, 1. Well, now let us check whether U and V is orthogonal or not. If you are asked this question, how to check that? You will simply calculate what? You will calculate the inner product of U and V, right? So this is what you have to calculate. So this way it is written, right? Now this is column means it is a ket one, but this is ket not ket u, it is bra u, so it will be dual of this thing. So it is a 1, 0. In the column will be now replaced by the row. Okay, and once complex conjugate is here, which is 1 itself, and 0's complex conjugate is here, which is 0 itself. Okay, which means if say if it is 1 plus, what I wanted to say is just a small case, don't get confused. If u is say 1 plus 2i and minus 5, okay, then ket u will be 1 plus 2i complex conjugate and minus 5 complex conjugate. So which is here it is minus 5 itself, and here it's 1 minus 2i. Okay, so it is basically the complex conjugate one. That is why it's called a dual. But since one's conjugate is 1 itself and 0's conjugate is 0 itself, we just writing the column like column 1, we are replacing with the row vector 1, 0. And V is ket V itself, so it will be as it is 0, 1. You got it? Row column form, which is the inner product form. I told you row column together is the inner product form. Just do the multiplication. 1 into 0 is 0, plus 0 into 1 is 0, which is 0. Since it is 0, therefore two vectors are orthogonal to each other. First condition is proved. Okay. Now second one is if they have the unit length or not. Just check it. It's of course unit length because it's only 1 and 0. It's 0 and 1. So it's also unit length. That property is also being satisfied. Like both U and V have unit length. It is U written in this way and V both are 1. Therefore, U and V are orthogonal and orthonormal. Orthonormal means automatically it's orthogonal. Still, I'm just writing it. But few example when say u is, say example 2, this is example 1. If u is 2, 0 and v, say for example, is 0 and 5, okay, then just check it. This one will be what? 2, 0 and 0, 5. So it's 2 into 0 plus 0 into 5 is 0. Therefore, they are orthogonal. But are they orthonormal? No. So orthonormal property is false, but orthogonal property is holding. But it is not normalized. That is why it is not orthonormal. Okay. So in order to make them orthonormal, what you should be doing? You should normalize it. So this is the way. To do that, it is okay. And similarly for v, sorry, the vector scalar vector. Then it is ultimately, then after, once you do this, then we will say u and v are orthonormal as well. Once you have done, sorry, ortho, just orthonormal. Okay, just tell me one thing. Till this part, is everything clear? These are few theory, few maths, all those things. Great. Orthogonal and orthonormal inner product, how to calculate it, the real like matrix calculation, all those stuff clear, right? Great, great. Because everything is so much interrelated. If anything here is stuck, you're stuck at somewhere, then the entire chain you will be stuck. That is why I just told you to put more focus. Now, once we have understood that what is orthonormal property and orthogonal property, now we will now head towards the orthonormal basis. Just a quick pause here. Why we are doing all those stuff? Are they really very, very relevant to our discussion or relevant to quantum computing? Absolutely relevant, because every quantum state is nothing but an orthonormal basis state. Whether it's a pure state or it is a superposed state. So if someone tells you whether all quantum states are orthonormal basis states or not, your answer should be that yes. Because quantum states have to be on a Hilbert, it has to be a part of the Hilbert space. Okay, and it has to be following the orthonormal property, and it will be an orthonormal basis. Okay, so now we will head towards the orthonormal basis. A set of vectors En. Remember, that was the proof that we are slowly heading towards. So in that way, we are just gradually making all the building blocks. So a set of vectors in a Hilbert space is called orthonormal basis if it satisfies two conditions. Okay. Condition number 1, orthonormality condition. Okay. What is that condition? That is En and En. They are inner product. This is inner product. I need not to now mention it. This is inner product of Em and En. This is delta Mn, or it's often written in this way as well, n comma n. Anything you can follow, either this or this. And this is equals to 1 if m is equals to n, and it is 0 if m not equals to n. This is super easy. But actually the definition seems this. Let me just show you why it's very easy. What does it mean? That is, if EM and EN are same thing, then it's 1 ultimately, otherwise 0. This much of an easy thing is actually like written in a very formal maths way. That is why you can see all the delta and all. Delta can be either 1 or 0 depending on whether m is equals to n or m is not equals to n. And it will always be true. It will always be true. And let me give that small proof again. See, I'm assuming something. You have to right now assume, but by the end of today's class, or maybe tomorrow, if it is space for a few more minutes, definitely will understand why I'm assuming this particular thing. I'm just assuming that K0 is a part of quantum state, but right now also I'm assuming it. Say K0 is 1, 0. Why it is 1, 0, why it is not 1, 1, all these things I will explain later. Only this much you assume, nothing else. So K0 is 1, 0. Okay. And so K1 is 0 and 1. Only this one you assume for now. Now just check whether what is the value. Say I'm just calculating K0, 0. So what it will be? It will be first 1, 0 row vector, 1, 0 column vector. Multiplied, it is 1 into 1 plus 0 into 0. Equals to 1 itself. Right? So if m and n are same, then it is delta mn is equals to 1. Proved. Second one. Similarly, for 1, 1, you can definitely understand it's 0, 1 into 0, 1. It's 0 into 0 plus 1 into 1, so 1. It's also proved. So for m equals to n, these two cases shows it is there. This is only quantum technology, sir. And if you specifically asking for quantum hardware part, so that is not at all there under the scope of QT-02, nowhere. It's purely the software, even the quantum information science also. So for real essence of quantum, I don't know what you are referring to by quantum technology. Quantum technology, if you are asking for quantum hardware, interpret technology as hardware, there is a section in QT-01 where several physical machine descriptions, what are the technology like topological qubits, photonic architecture, all those things were partly discussed. So you have to refer that video. Otherwise, all these things we are doing is the same thing. Today is your first class. I got it. I got it. I got it. Just at least the one thing, whatever yesterday I covered, that's the first class of QT-02. Please have a check on that. Don't miss any classes here. It's very difficult for you then to follow. Dr. Mani, I guess someone, Mahipala or someone, I guess. So he also was referring the same thing, that you cannot skip any class for quantum. It's very difficult otherwise. Please check to yesterday's class. Okay. So it is if m is equals to n. And if m is not equals to n, that is, say, 0, 1, then raw 0 is nothing but what? The row vector 1, 0. And this one is a column vector 0, 1. What it is? 1 into 0 plus 0 into 1. 0. So check if m and n are not same, then it is 0. So this is delta mn when m and n are not equal, and this is also delta n. But since we are defining it, formula, etc., so that is why we are writing this. Then this is called orthonormality condition. I hope the definition itself is now clear along with the example. This is the first condition for vectors, for a set of vectors to be an orthonormal basis. Okay. The second condition is the completeness condition. Completeness condition. What does it say? That any vector psi in the space means the Hilbert space, can be written as any vector psi in the Hilbert space can be written as psi is equals to sigma n alpha n times En. En is what? It is a orthonormal basis. right? And alpha is what? It is some sort of coefficients. So to be very precise, alpha n is nothing but En, inner product of En and psi. It is the same thing. Remember one mantra for quantum. Wherever you stuck with the abstract symbol, you stuck with the theory. You're referring some book, you're referring some good paper. Somewhere you are stuck. You're not able that what is you're not able to understand what is the interpretation. Simple one mantra is just break it down. Just like in multiple choice exam, IIT exam or any exam, we do it. Like whenever we do not know it, we just check with the options itself and just try to eliminate. So similarly do this here as well. Just try to break it down into the basic of the basic components. So here what components will you be getting? Ultimately the addition and the multiplication and the vector, all these things itself, and a bit of algebra. Very less, minimum amount of algebra. Very minimum amount of algebra, like normal algebra, then probability and probability distribution functions. Gaussian, very, very basic distributions, Gaussian, binomial, all these things. Okay, I think these two are most widely used. What I actually found. All those things I know that every one of you know already. Except that it's only about matrix, linear algebra. Only that thing. Break it down. You are not understanding it, just break it down. Take an example and break it down. Then you will be able to understand or decipher the underlying theory. And this is the only way out. Just take a pen and paper and do all these things. This is the only way out. No matter how good book you refer to, if you do not understand this thing, you can never crack. You can never crack. This is a very honest thing that I'm telling. Okay. So En was your basis. Alpha n is your expansion coefficient. So psi is any vector in the space that can be written in that. An example is in quantum right now only after maybe few minutes we're going to discuss in that way. So that's why I'm just writing it. Say, for now assume that 0, 0, what is 0, 0? It's not very important, but just as of now take it for granted. These are basis states. That is there your En, right? All of them are En. So En, writing this is equivalent to writing this thing. Familiar with the notations, right? Same thing itself. Basis states is En. Each state is En. Set of Ens is basically within curly braces I'm writing. So both of them are same. So phi, this psi is, now you can write it down. Oh, how it can be negative? How it can be negative? It's a normalization condition, otherwise it will not follow. And I will come to that. Wait. So psi is alpha n. Alpha n is the expansion coefficient. So anything which can be, right now, let me take it as alpha 1. So sigma, how many basis states are there? What is the value of n? What is the value of n? 4, right? So sigma is 4, n equals to 4. So it's alpha 1 E1, which is 0, 0, plus alpha 2, 0, 1, plus alpha 3, 1, 0, plus alpha 4, 1, 1. So a vector itself psi, it can also exist. Now it means if it is a Hilbert space where 0, 0 were somewhere 0, 1 here, say 1, 0 here, 1, 1 here. So K psi also can reside here. And if you closely follow it, it shows some sort of some sort of superposition. Because this is a quantum state. This is a quantum state. That is a basis state. This is a quantum state. This one is also a quantum state. All of them are residing in the Hilbert space. And psi, it is also a quantum state. Only difference is this is a pure state. This is a pure state. This one is a pure state. And this one is also a pure state. But this is a, sorry, this is a superposed state. Okay. Got it? So this is the completeness condition. The first condition was orthonormal condition. That was this thing. And second is here. Okay. Now that we know orthonormal basis, now thing is why to choose orthonormal basis in a quick theory? Why to choose orthonormal basis in Q mechanics, quantum mechanics? Point number one, probabilities are well defined. Point number two, measurements correspond to projections. Point number three, superpositions follow linear algebra rules. Point number four is the expansion coefficient alpha n have a clear probabilistic interpretation. Where alpha n square probability of finding just a minute. I guess there is certain confusion with the negative. I'm just coming to that point. Probability of finding, but I don't know whether you are discussing among yourselves or not. Probability of finding the system in state En upon measurement. Okay. So assuming these En or a set of these basis state vectors in orthonormal basis and psi is any. System means not a quantum particle, it means a quantum system itself. Particle I'm referring. Basically, quantum state can be a quantum particle itself, or quantum state can be a set of quantum particles which are within some quantum states. So it can be a superposition of that as well. So that we say refer by a system. Say, for example, I'm referring as a 2-qubit system. So here there are different quantum states, each incorporate different number of qubits. So 2-qubit quantum state or say a 2-qubit quantum system has a few number of quantum states into it. So it's overall a quantum system that I'm referring to. Okay. So assuming this is orthonormal basis and psi is any arbitrary state, we can write that implies that psi can be written in this way. Okay. Now at this position, let me mark it equation number 1. Equation number 1. On equation number 1, now I will take inner product of both sides with respect to EM.
Very difficult to use WebEx. Directly they are not getting feedback है सर JNU का participant से. Very difficult to use this WebEx process. Registration. Every time they are searching for link, it is going to mail spam folder.
थोड़ा आदत हो गया तो
मैंने बोला कोर्स कोऑर्डिनेटर को बता दीजिए आप.
प्रिंसिपल कोऑर्डिनेटर
Sir, I think someone of you is not muted.
But here, how to collect attendance? Again, we send attendance link. Needed,
Yes.
I hope now they are muted. Okay. Yeah. Okay. Now, this is equation number 1. Okay. Now, what we are doing is with respect to EM. This is EM. With respect to EM, we are applying inner product on both sides. So let me do that. So taking inner product of both sides, say both sides with this EM, what we will get? Okay, initially, let me just write it once again. It was this alpha and EM. Now we are applying it. So it's EM psi is equals to EM then sigma n alpha n En. So bringing this thing outside alpha n, and we can do that because it's just a coefficient, nothing else, which is nothing but alpha n square is probability. Okay, so just refer it. Alpha n square is probability, which is ultimately some scalar value. So we are just taking it out. So it's alpha n, then inner product of EM and EN. Okay. Now, what is inner product of EM and EN? Have you seen that? Yes, we have. Where it is exactly, here, orthonormality condition. EM, EN, inner product of them is nothing but delta MN, right? So let me just write it down. So it's sigma n, alpha n into delta MN.
इसमें सारे लिंक मिल जाएंगे आपको.
Okay.
किसी के नाम भी मिल जाएंगे.
Also, just one thing, this delta MN is known as Kronecker
ये joining link
delta, where delta Mn is equals to 1 for M is equals to N, and it is 0 for M not equals to 1.
ऑनलाइन नहीं है, गलत कर
Okay. What is the time now? Time now. Can anyone just tell them I will not use it right now?
अक्का
3:33. Thank you. Time now. Okay. So now on applying this thing, the delta function will do what? On applying this, the delta, because for few values it will cancel out. So understanding it, right? Where? Because inner product of 0 and 1 is 0. So similarly, inner product of 0, 0 and 0, 1 or 0010 or 0011 will also be 0. Only inner product of 00 and 00 will be 1. So when 00 is associated with all other values except 00, everywhere delta is basically killing all the terms except where n and m both are equal. You are getting it? If it is true for 0 and 1, then it also for for two states, for 0, 0, 0, 1, 1, 0 and 1, 1, if I increase it, that is 0 and 1 initially there was. Now if I increase it, sure. Okay. Let me give an example. Let me just write the definition. Then I have the delta function kills off all the terms except when your n and m are equal. So the sum will become alpha m only. Let me give you an example. We'll understand it. See, psi is, say, alpha 1 E1. Let me take this thing, plus alpha 2 E2 plus alpha 3 E3. Only this one. Now you take inner product with except of m and n, all those things. I'm just writing 1, 2, 3, 4 likewise. You take inner product with E2. That means with this thing. Then it will be apply inner product on both sides. So this thing. So it will be E2 alpha 1 E1. So I'm just writing alpha 1 over here. So it's E2 and this is E1. As alpha 2, I'm taking it out. So it is E2 and this one is also E2. Alpha 3 E2 and this one is E3. Right? Now, except E2, E2. Only this one will be 1. This is 0. This is 0. So what I'm getting only alpha 2. See here. So whatever I'm taking here, both of them are equal. Right? The coefficient itself. This thing and this thing. So that is why I have written that it is ultimately alpha m only. Why? Because I have taken with respect to em. Okay. That's the thing. Therefore, we can say that alpha n is en. If it is same for alpha m, it is also same for alpha n. So we can write alpha n equals to inner product of en and psi. This is was the expansion coefficient as per the definition. Just do a check. And this was the basis state, and this was the entire state, the superposed state or the big state which comprising all these particular basis states. Okay, and this is alpha n. This alpha n is basically also the projection. You can see it's like a projection of en on psi, which is giving me alpha n. That means it's kind of a projection that gives or tells me where my particular basis state or desired basis state is in the superposed quantum state. So it's like a projection from a fixed value. Now I want to find it out that where in the big space, where exactly my match is there. It's kind of this thing. So it's like here, it's a E2. It's ultimately trying to find in a space where it's kind of a projection. This is a match with E2. Maybe here you are, here E4, here E3, all of them are present. So it's kind of a projection. And this alpha n is also called as a probabilistic amplitude. Remember, probabilistic amplitude is not probability. Probabilistic amplitude is square root of probability, because if alpha n is this, or projection is this, then alpha n square gives me nothing but the probability of measuring or obtaining, whatever you say, obtaining state En in psi. This is the probability. So the probabilistic amplitude is alpha n and probability is alpha n square. These two is extremely important. Just always keep it in mind that alpha n is the projection, it is the probabilistic amplitude, and then instead of directly writing the value, we have seen that how and why it is a projection. Okay, ultimately E2 and phi, E2 and psi, their inner product is giving you alpha 2. Similarly, if you do it with E3 and psi, inner product of E3 and psi, when E3 is the third basis state, psi is the superposed state, then we will be getting alpha 3, which is the projection of E3 in psi. And alpha 3 square is the probability of obtaining E3 in psi. Till this part, it's clear. The probabilistic amplitude, alpha, inner product, all these things. Great, great. Okay, and one I want to mention, one was asking that, okay, if it can be negative, there is no question here, because ultimately the 1, 0 and all those things, they represent something. They represent the existence of a particular state. So here the amplitude is not important. So whenever, though it is -1, but ultimately that minus here signifies the phase. Minus here is not associated in quantum. No negative sign, except some of the like normally except some of the maybe amplitude or something. Some very deterministic calculation, deterministic amplitude, wherever I'm bringing. That's a different thing. I'd say I'm calculating the mean of the or average of something, then I'm just deleting, adding something, some sort of algebraic or arithmetic operation I'm doing, that is okay. But otherwise, whenever I'm representing something in form of a quantum or to represent a quantum state, here if I put a minus, that means it is associated with some phase. It is not associated with amplitude. And that will not come into consideration for the inner product cases at all. Okay, that is why it is there, that whether that it can be some scalar value. Nothing else. Generally, it will not. If you found some case, then just let me know. But it should not. Okay. Now, next postulate we will head towards. Let me just target. My target is to cover Copenhagen interpretation. At least to give you some essence of it. Then observable and operator, matrix equivalence, and adjoint and Hermitian. At least that is the target. Let me see that's how much we can cover. So Copenhagen interpretation of quantum mechanics is a story that happened near somewhere around late 19th to early 20th century. There is a place in Europe called Copenhagen, and they're all like several scientists, they gathered to discuss and formulate few of the interpretations of quantum mechanics. So all of them are called standard interpretations, and later they were renamed as Copenhagen interpretation, because it was in Copenhagen itself they discussed and they discovered that kind of a theory. Okay, the state vector, and what does it state? Copenhagen interpretation, it states that the state vector psi only has a probabilistic interpretation. It has a probabilistic interpretation. not a deterministic. That was the fundamental thing that we were discussing yesterday, that here everything is a part of the probabilistic reasoning, not a deterministic mathematical model it uses. So it's a probabilistic interpretation. Okay. Now, also, if psi can be written in this way, say C1, C2, C1, C2, and all these things are like complex values, complex numbers. Okay. And then dual of this thing, so this is nothing but C1. I just explained it, still writing it formally. And real number is a subset of complex number. Likewise, it is same thing. Okay, so if it is 5, it will be 5. If it is 1 plus I, it will be 1 minus I. Same thing. I discussed. Okay. Now, postulate 1 here under this interpretation is the vector, any vector to matrix transformation. Vector is equivalent to matrix. Now, a few theory I want to discuss. This is QT-0. One asked that why we use QT instead of bra notation everywhere, because mostly the QT notation is a building block for an operator. Whenever it is, I will show probably today itself. QT notation is primarily useful to build up a quantum operator. Now, if we because of simple the matrix multiplication, it is a column. It's like a column vector kit, right? So once a quantum state, it's always in a power of like either it's a 2 cross 2 or it's a 4 cross 4 or it's a kind of an 8 cross 8. So we want to get another matrix, and that is why we take the cat notation, because the quantum state, the way it evolves, follows this particular format. In order to get the matrix format, we need the cat notation. So bra notation are mostly used for in somewhere in between for something, maybe to calculate the expectation value, to calculate the projection, to calculate those stuffs or inner product, all those things. Okay. So this is QT-0. This one is QT-1. Let me now tell you the interpretation. Just few minutes back, I told you that QT-0 is 1, 0. What does it mean? It means that here 1 means my 0 is on. And here 0 means my 1 is off. So this is the position for 0. So here 0 means my 0 is 0, and here 1 means my 0 is 1. Similarly, in the bottom, this is a position for 1. So for QT-1, it is nothing but 0 and 1, which means my 1 position is 1, that is, it is 1 is 1. Okay? Now, similarly, now just tell me if it is something in a vector, this is a vector form, this is a matrix form. Now I'm just translating between these two. If it is 1 and 1, what will you interpret? You will interpret it in this way. Now see the essence of superposition, how to interpret it whenever it's in a matrix form. Yes. So what I just explained it. Please focus here. I explained this is a quantum state. QT-0 and QT-1. A quantum state can be in a pure state. So QT-0 and QT-1. Just like a classical. Here instead of only 0, I'm writing QT-0. Instead of only 1, I'm writing QT-1. It means now QT-0 is nothing but a column vector for representation of 1, 0 in this way. Here 1 means it signifies that my 0th position is on. 0th position is on. And here it says my 1th or first position is off. Similarly for QT. So 0 1. Now if both are 1, 1, what does it signify? It signifies that there is a, in position of 0 also there is a 1, in position of 1 also there is a 1. So it states that it is a superposed state. What it is? It is a superposed quantum state. which can be written in this way, that I do not know what is my alpha. That can be any alpha, or say alpha 1 times kid, or say 1 0 plus alpha 2 times 0 1. Alpha and here also alpha 1 and alpha 2 are not considering, so scalar 1, but ultimately 1 0 plus 0 1 has been added up together and we have from 1 1. This means it is alpha 1 get 0 plus alpha 2 get 1. And this is get psi. So that states that any arbitrary quantum state which can be in a superposition that exists in a Hilbert space along with 0 1 psi also can exist. The same theory. Thus theory and practical they actually mapped, where it is basically a superposed one. So alpha 1 get 0 plus beta 1 get 1. Or say anything, alpha, beta, or gamma, whatever it is. Okay. And if it is, let me now itself explain it. So this is called a 1 qubit system. So 1 qubit quantum system. System is what I told. Quantum, 1 qubit. And now a new thing will come, that is a quantum state. So what do I mean? 1 qubit means I have only one space. I have only one qubit. A qubit is what? A qubit is simultaneously, it can be 0, it can be 1, it can be combination of 0 and 1. It can be anything. So it has three different possibilities. Either it can only be 0, or it can be purely 1, or it can be 50-50% or some percent of 0 and 1 both. Which means if I write psi is a quantum state, it has 100%, it is only say at 0. That means 0 state has 100% probability. If I say psi is equals to 1, similarly it says at 1 has 100% probability. Now if I say this is 50% times 0, here I'm writing in percent way. Do not get confused with probabilistic amplitude and probability. You have to accordingly adjust. Okay, for simplicity, I'm just writing it in this way. And 50% 1. This is also a quantum state. All are valid. Now you should ask me. So this is a quantum state. This is a quantum state. This is also a quantum state. Now, if I ask you, then can you tell me that what is the maximum possible quantum states in a system, in a 1 qubit quantum system? Right? So under superposition, if I say under superposition, no, it's 1 qubit. 1 qubit only. So in 1 qubit, it is maximum 2 states that can exist in superposition. So with 1 qubit system, we can maximum represent 2 states. But this is a superposed quantum state. This is a pure quantum state. This is a pure quantum state. But 1 qubit quantum system can hold maximum 2 states, which is K0 and K1 together. This is a representation, and this is a maximum count of that state under superposition. Under superposition. So if you do not superpose the 5-finger theory that I just explained yesterday, if you do not superpose, you say I am not using my thumb, I am only using the other remaining 4 fingers. 1 is not in superposition, only 4 is in superposition. So I can see the quantum effect of superposition or the parallelism with respect to 4 fingers itself. Now I am stating, say I have only 1 thumb. I have 1 qubit, so I have 1 thumb. It can be either up and down. So how many maximum states can be in superposition? Answer is 2. Simple. Either up or down. So I can encode maximum 2 units of information. If I am able to encode, one I will encode for up, one I will encode for down. Now similarly, if I have a 2-qubit system, two-qubit quantum system means I have 2 qubits. So it can be 0 or 1, it can be 0 or 1. That is the maximum number of states possible under superposition. 1 qubit means only one register. That register can be 0 or 1. So under superposition, it can hold maximum 0 and 1. That is what I am telling. Okay, don't get confused. This is either a scenario when it is only holding a pure state. This is a second scenario where it is only holding another pure state, which is 1. But this is a scenario when it is at some point, at an instance, simultaneously, whatever you say interchangeably, holding 2 quantum states, because that is what it maximum can hold if that qubit is a quantum register and it is in superposition. Okay, clear? This part is clear. So this is at a time. These are just the scenarios. This is either this or this or this. But when I am in this place, at max 2 states I can hold. That is a theory. Similarly, for a 2-qubit system, it's a 0, 1 and a 0, 1. I have 2 fingers, only 2 fingers now. So what is the maximum probability possibility? 2 to the power 2, that is 4. And what are those possibilities? 0, 0, then 0 and 1, then 1 and 0, and this 1 and this 1. So this is a quantum state, this is a quantum state, this is a quantum state, this is a quantum state. So at maximum, when there is a superposition, there exists symbol, there exists superposition. The superposed quantum state, not states. There is only one superposed quantum state, say psi, can hold maximum 4 basis states. And how it will look like? Alpha K00 plus beta K01 plus gamma K10 plus delta state of the system. I guess. Okay. So all these are pure states with respect to a 2-qubit quantum system. So how many systems is there? Only one system. That system comprises of what? That system comprises of 2 qubits. So what we will call it? We will call it a 2-qubit quantum system. Okay. So put your S very carefully. It's a 2-qubit quantum system. It can have maximum how many possible states? It can have maximum 4 basis states. What can be those states? 0, 0, 0, 1, 1, 0, and 1, 1 if I represent it in binary form. If I want to represent in decimal form, I can also write it down in this way, considering this is in decimal. Generally, we don't do it, but if you somewhere see this thing, don't get confused. Just convert it to binary. This is the same thing. Okay, so it's a 1 quantum system where number of qubits is 2. So there are 2 quantum registers. Clear. On the 2 quantum registers, with those 2 registers, how many quantum states maximum can exist as basis states? 4. What are the states? 0, 0, 0, 1, 1, 0, and 1, 1. If I include all of them and incorporate a superposition through some quantum gates, okay, then that superposed quantum state will be how many? Only 1. If I incorporate all of them together, there will be only 1 superposed quantum state now. So now the individual basis states will not exist anymore. keep this thing in mind. This is the fundamental shifting in thought process. Once you superpose something, you have to think every operation in a way that it affects all of your individual states now, because you cannot do anything or anything explicitly on any of the selected basis states if it is in superposition. If you want to do a particular operation you want to do on QT-10, you cannot do that once you apply superposition. And what will happen if you do that? It will break your superposition. So you again have to incorporate that thing into your superposition, then you can do that. So if you want to see, or if you want to include 4 units of information, then, and at a time you want to do something with all the 4 units, then you cannot explicitly think of doing any operation in a superposed state on your desired state. That is not possible. So you have to do everything. Whatever you do, you have to do it for all. It's just like you have, say, 4 kids now. If you want to give 1 chocolate to 1 kid, you have to give it to all. If you want to like scold someone, you have to scold all the other children as well. That is how you have to slowly, very slowly, you have to do the evolution of your quantum state or quantum system, which comprises of these basis states. Right now, they are in superposition. Definitely, out of 4, say, if you have 2 qubits, you can keep 1 qubit into superposition and 1 qubit you can left as it is. Then that as it is left qubit will behave as a pure state, and 1 which is in superposition can hold 2 states. Likewise, it will happen. Okay. I guess today we are with the time. Time is already. What is the time now? I don't know. Let me know what is the time. Exactly, it's 4. I've not checked it.
It's 4 p.m., ma'am.
Okay, okay. So only one more thing, since I described this thing, just today, I will pause here. The Hermitian and all those things observable, I will cover tomorrow. Just one thing, just give me 1 minute. Just like QT-0 is 10, remember the position? It's nothing but the position. QT-1 is 01. Similarly, it's also the representation of some position. This is for a 1 qubit system. Whenever it's a 2 qubit, that is this thing. Just verify the position. I'm writing the vector form or the matrix form. I am giving you the schedule. So 00 is nothing but 1000. So 008th position is on. Okay. 01 is 0100. 01th position is on. 10 is basically 0010. 10th position is on. This is 108th position. And 11 is 0001, where 11th position is on. We will be talking, let me just write it down. We will be talking about the operators, the basic of operator. It is not quantum gate. Again, the theoretical description of the operator, where definitely the one just you mentioned, tensor product and all the stuff. So now, right now we have seen only the inner product. So the outer product form, which is the QT form, that I will be talking about. Okay. Followed that, it will be the adjoint operator and the Hermitian operator. But the Hermitian is also self-adjoint. Okay. Okay. Hermitian is done. This is done. Matrix direct form. Then we will head towards the more things of these. The above 0th position is on. This one you are referring for 00? I guess so. So it is 0th position is on. And here it's 0th position on. Just the position, nothing else. So it's 0, 1, 2, 3. 0, 0 means 0. So 0th position is on. Here 0, 1 means 1. So 1th position is on. Well, 1, 0 is nothing but 2. So 2th position is on. Okay. And 1, 1 is 3. So for 3, the 3th position is on. Nothing else. This class we will again continue with the postulates. Quantum postulates. And of course maths. But not to mention. And slowly, if time permits, then we will enter. We already entered today itself. See, we have to do a mix and match. Only qubit we will do later, but bracket notation we'll be doing here. It's not possible. So ultimately, it has to be a full-fledged understanding. That's it. Yes. Okay. Syllabus is what you already have. This is the way, these are the like sequences that we will be covering. Syllabus, you can ask from Pilli sir or anyone.
Syllabus is already shared in the WhatsApp group. If you are not there in the WhatsApp group, please join. I will anyway send one email with all these contents and the links. So don't worry. Quiz will not be every day. After madam completes her course, one quiz will be there. Jai Kumar and Rahman sir, both of them when they cover, one more quiz. And lastly, after Dr. Ashwath Babu completes the course, one more quiz. So totally we are scheduling 3 quizzes. You will have to get 40% in aggregate in all the 3 quizzes put together, right? So I hope that should be fine. Don't worry about quiz. Quiz is not every day. Attendance will be directly taken from this one, right? WhatsApp will be coming by email. Please check the email and join the WhatsApp group. I don't know. Please read the email. Please see the PPTs or PDFs that are attached. Please see them. We cannot give instructions. I've been doing, but then please read the email, confirmation email. Please read what you are expected to do. Unfortunately, slightly difficult here because we don't want to send another link for attendance, another link for this, another link for that. WebEx will give the attendance, and we will copy it there, and then you can check it out. And then we are using Canvas, and we are using Canvas to link up, right? So that's where you are. There is one small request for all of you. Madam is sending one link. Okay, please send. It is there on the chat. Right? So kindly all of you click on this link. This is a link for World Quantum Day. We are just doing a trial. Please all of you give us 10 minutes. If all of you join, we'll be able to test it, right? Microsoft Teams will open. If you don't have the software, don't worry. You directly can open in the browser, right? So you can go there, right? So let this also run, let that also run. Anyway, please note before you go there, please note that tomorrow is Sunday, so no class. Day after tomorrow is Monday, Ambedkar Jayanti, no class. And on Tuesday, we'll have the World Quantum Day celebration by AICTE. So other guests will also be there. So we will join on this. Second wala copy.
Thank you everyone for today's class, attending to this class.
Thank you. Thank you so much, ma'am, for the time. Thank you, Dr. Ashwath, for joining.
Thank you, Dr. Pili.
Yeah.
Thank you.
Yeah. Thank you, ma'am. We'll meet on 15th, ma'am. Please, you also join. Yeah. Thank you.
Sure.